for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Okay, so thank you everyone. Hello everyone, thank you for joining us today and welcome to today's webinar from our Standards Activity Board series and today's presentations from the 802.11 working group. My name is Edward O. I am the Vice Chair of the IEEE Computer Society Standards Activity Board. Before we get started, I would like to address some housekeeping items with all of you. This webinar is being recorded. You can ask any questions in the Q&A box you see on your screen. The speakers will answer as many questions as possible. When submitting a question, please reference the slide. The goal will be to allow for a quick question or two after each presenter, and then we will bring all of the three speakers back online for a formal Q&A at the end. A copy of the slides and the recorded webinar will be emailed to you tentatively tomorrow. Standard IEEE 802.11 is just one of the many standards founded by the IEEE and IEEE Standards Association that you can learn more about. Keep up with our ongoing calls for participation and get involved with the standard board activities of our society. Our IEEE Computer Society is a global community where you can learn more about this standard and discover more. And as part of this network, you have the opportunity to connect with professionals from all over the world. Expand your knowledge with the Computer Society Digital Library, which features over 500,000 papers and articles, highlighting the latest in networking technology research. Furthermore, you can go with other professionals through many different kinds of events, such as technical communities, conference, and student chapters. Information will be shared also after the webinar, and you can learn more about at our official website, computer.org. Now, circling back to our today's presentation with our three speakers online here. As many of you may know, Wi-Fi is important to any of us. The 802.11 working group, which is managed by the IEEE Computer Society 802 NAMAN Standard Committee, focuses on developing these cutting-edge standards for wireless local area networks. Actually, you may hear lots of useful and practical applications about 802.11, and you may actually now using your laptop to connect to Wi-Fi, which is also developed based on the 802.11 technologies. And in this webinar, we're happy that we will have a live discussion with the officers here about their work. And now, first up is Ms. Dorothy Stanley. Dorothy is an HPE fellow and head of the Standards Strategy at Aruba, an HPE company. She currently serves as the chair of the 802.11 working group, and she has chaired several task groups inside the 802 working group and also served in numerous leadership roles in Wi-Fi Alliance. She is currently a member of the IEEE Standards Association Board of Governors, and she has held past roles on Standard Board and as a chair of the IEEE Standards Association New Standard Committee. She has worked on multiple networking technologies and protocols in both wired and wireless networking, and he has many awards from Wi-Fi Alliance and also as a Standard Association. Dorothy, thank you very much, and we are happy for you to be on board with us. And you now have the floor to give our audience an overview about the 802.11 standards. Thank you, Dorothy.
Thank you very much, Edward, and thank you and the Computer Society for the opportunity to present about the standards that we are in the process of developing. So I'll give an overview of 802.11 standards and the development, and then we'll have go in more detail about two of the amendments that will be published very shortly that you see here, 11BB, like communications, and 11BC, which deals with broadcast services. So first, some context on the Landman Standards Committee, our area of focus for our work. So the whole Standards Committee focuses on link and physical layers in the network stack. So we are here in the data link and PHY layers. You see 802.11 highlighted in the green circle. The other groups active within 802 are shown here, 802.1 and .3, .15 I'll highlight in particular. So .3, they develop Ethernet standards, very widely used, along with our Wi-Fi WLAN standards. I'll highlight also 802.1 and the arrow that shows TSN. TSN has to do with time-sensitive networking, and this is a very active area of standards development for many different applications, especially industrial and automotive. While the focus in the past has been on wired applications for time-sensitive networking, the focus is growing with additional work in 802.11, focusing on increased applications of time-sensitive networking over wireless networks. The other point I want to make is that especially for 802.11 protocols as well as .3, we leverage IETF protocols for the upper layers. And I think this is one reason why the technology has had significant success, that additional adaptation layers or intermediate focus points are not needed. So I'll summarize each of the task groups that we have currently active within the .11 working group. We continually complete work and then start new work on new topic areas and new standards and new amendments to further increase the capabilities and the number of applications and types of applications that can be supported with the technology. So we'll focus in more detail on the two that are highlighted here. 11AZ, we just completed that document just published recently on next generation positioning features. Now, what is positioning? So positioning and ranging and location determination is becoming more and more important for new applications. And the amendment that we completed with 11AZ enables centimeter level accuracy in applications, which is a order of magnitude improvement over what the technology currently provides, which is meter level accuracy. That in itself does support a lot of applications, such as wayfinding in indoor applications. Enhancements for next generation V2X. This document also just completed. So we do have a standard developed on the order of 10 years ago, a little bit more, for vehicular applications. And this 11BD standard takes some enhancements that were included in intermediate amendments such as 11N, 11AC, and adopted those for the vehicular application. The primary use of this standard is in Europe. An area that we're spending a lot of time on is 11BE. This is the major, in terms of number of people who are involved, looking at further enhancements in our bread and butter bands of 2.4 and 5 gigahertz, as well as the newly opened 6 gigahertz band, which is incredibly important for the growth of the technology and indeed the economic value that can be added by .11 networks going forward. 11BF focuses on wireless LAN sensing, and this is a new application using the RF medium of .11. So traditionally we use the medium, the radio interface, for delivering information, right? Delivering data and all of the various applications that data enables. This is a new application where by sensing the characteristics of the RF really tool to be used for many, many different applications, from opening a laptop once you're near it, or determining whether there are devices or individuals in a particular area. One topic that we focused on here was privacy and making sure that there's an opt-in mechanism if this is going to be used. 11BH and 11BI focus on the use of random MAC addresses, which is something that is quite widespread now and is becoming really just a de facto way of using MAC addresses. And so there are a lot of applications that had been developed there that now need new tools. And then enhanced data privacy, making sure that there's nothing that can be gleaned from the frames that are exchanged over the air. And then 11BK, which is 320 megahertz ranging, additional improvements in location capabilities. So these are all of the active task groups. The next slide shows the evolution in capabilities. I won't go through this in great detail, but you can see the growth over time of the data rates that are supported over the wireless link. And this enables new applications, video, etc. The products that are shipping now in the marketplace are based and marketed via efforts of the Wi-Fi Alliance on Wi-Fi 6 and 6E. Wi-Fi 6 refers to 11AX, and 6E refers to use of the 6 gigahertz band, which is becoming more and more available throughout the world. This standard focused in these 4 technical areas that you see here, each of which brings significant benefits to deployment of the technology. Power saving is always of import, and we really have a roadmap, if you will, of features to continually reduce our power footprint in use of Wi-Fi, and also outdoor and longer range. A key application and use of Wi-Fi networks, .11-based networks, is for connecting the unconnected, for community networks, for outdoor applications, hotspot applications. And here, the longer range you have, the lower cost the deployed network can obtain. Okay, so in Wi-Fi 7, which is coming to the market very soon, we focus on throughput and spectral efficiency, on low latency, and enhancements to support 6 gigahertz. This will be the next generation of the MAC-PHY technology, and this is very key for evolution of the industry. We're beginning work on technologies even beyond that, and again, high interest in this area. We're looking at continuing to improve the latency characteristics, the manageability, the throughput, power consumption capabilities of the technology. And we anticipate the task group for this work, which will be known as 11BN, to start in November. And there are more activities there. I'll finish by highlighting 2 topic interest group areas and study group areas where this is a way that we can look at, is there a sufficient interest within the members of the group and indeed application of the target technology that we can do further work in that area. We're looking at 2 areas currently. One is AI/ML, artificial intelligence machine learning. So there are some links here you can follow later, but there's been significant research work done in AI/ML and its application to .11 systems. So we're continuing to look at that and see if there are additional applications or APIs that we need to develop or make visible so that these systems and tools can be used to make the overall network and radio interfaces more effective and efficient. The other new area we're looking at, and this work has advanced to the study group phase, which means we're very likely to, in the future, form a task group to begin work in this area, is support of ambient power. So this is where energy is harvested from the RF in the area to power extremely low power devices for a number of the applications that you see here. A very interesting area of work. If you're interested in this, please do join us. And all of the topic areas are available online. All the submissions are available online for people to look at. So Edward, I will stop there. 6 gigahertz, of course, is important. And the final point is that we, as a summary, continue to enhance the standard with technical capabilities that enable new services, new business models, and the bottom line, to enable economic growth and access to the technology and the internet, which is the new utility that's essential for the modern age. So over to you, Edward.
Thank you, Dorothy. Thank you very much for the great presentation. Actually, there is one quick question. I'm not sure if it is quick for you to answer, but the audience would like to know how can they contribute or participate in your working group?
Okay. So in the presentation, you'll see additional slides here. Oh, no, we don't have that one. Okay. If you do a search on 802.11, you'll come to the 802.11 website, and the links are all there. We meet both in person and via teleconference for our meetings, our in-person meetings now, thankfully, which are 6 times a year. Between those meetings, we have teleconferences. So there's no charge, no fee or registration to attend the ongoing teleconferences. To attend the meetings, which are the sessions, which are held 6 times a year, you do need to register and pay a fee for those. But I would say look at the documents, look at the website, drop me an email. I'm happy to answer questions to point people in the right direction. But all of the submission documents are online. The links are on the webpage. So just go for it.
Awesome. Thank you, Dorothy. Thanks again for the great overview of the 802.11 working group. Actually, from your presentation, we understand that there are many parallel standard development activities ongoing in your committee. And thanks again for all of your work and your working group to develop high-quality market relevant standards that are very important to our society, computer society, the IEEE Standard Association, and IEEE. And we look forward to hearing more from you and your members in future. Thanks again, Dorothy.
Thank you, Edward.
And then our second speaker is Dr. Nicola Sevaminsky. Nicola has been working with major companies in Wi-Fi technology and commercialization to create a comprehensive ecosystem of relevant partners for the mass market deployment of Wi-Fi. Nicola is the current chair of the 802.11 Night Communication Task Group, also known as the 11BB. He is also a former vice chair of the 802.15.13 Task Group on multi-gigabit optical wireless communications, as well as a co-chair for the Night Communications Alliance. Nicola, thanks again for all the work and leadership you have for the light communications. Please, you now have the floor to share with all of us the great work of the job 802.11BB standards. Please.
Thank you very much, Edward. Thank you, Dorothy, for the introductions. So basically, the one great thing about IEEE is that literally every single contribution is available freely for anybody that is interested in reading. So when you see these documents, you see right at the top, there's an IEEE 802.11-23-028283R0. That is a document number to a database called Mentor that every single file is readily available, freely downloadable for anybody that is interested in reading it. So if you want to participate, please join us. Okay, so let's talk about light communications for a minute. The idea here is to just give you a high level of the need, the use cases, and a little bit about the technology that we're developing in 802.11BB, and of course, encourage you to participate moving forward. So Wi-Fi, unfortunately, has become synonymous for everything that uses light communication. So the first thing that we have to understand is when we're talking about 802.11BB, we are talking about a very specific subset. And there are really 3 different types of optical wireless communication. The first one uses the camera on mobile phones, along with slowly changing intensities of the lights in the ceiling to do positioning for devices. This is typically called optical camera communications. Then there's Li-Fi, which is what we mean in 802.11bb by light communications, which is high-speed, secure, mobile wireless communication, effectively providing a substantially similar experience to traditional Wi-Fi, just using the light spectrum. And the third type is really free space optics, where it's point-to-point, really, relatively speaking, long distances, high-speed communications. So we will focus on Li-Fi in 802.11bb. So what's the need? Well, basically, there's a ton of applications where radio frequencies are either not allowed or not usable for security or safety reasons. And that increases with complexity over time. So clear examples are, underwater communications or defense environments and secure spaces where radio frequencies can present danger to life, or it can be considered really a challenge for security experts to use it properly. You have data centers where really high capacity, high density is required, Industry 4.0 for robots in a very harsh environment, lots of propagation, lots of issues with signaling, especially in the lower bands of the RF spectrum. And then, of course, office and commercial spaces, as we start using up a lot of the free capacity. Now, fortunately, there's more with 6 gigahertz space, but sooner rather than later, consuming at an exponential rate of spectrum, we need more spectrum, and that's where light comes in. Of course, there's retail and finance for indoor locations positioning, smart cities and transportation, and eventually into the consumer everyday lifestyle. So there's a lot of use cases where light can help provide better connectivity or more robust, and definitely provide higher levels of security and sensitivity. So what does it do? Well, it's bidirectional, so it's using light both for the downlink and the uplink. It is mobile, so you're expected to be able to move from one access point to another or from one light to another. And you can get significantly higher data densities with light relative to traditional RF, and of course higher quality of service because you have guaranteed effectively clear channel all the time. Very robust against jamming. It's very important to note that this is not replacing RF. This is complementing RF to extend the wireless experience everywhere we go. It's synergies for providing a combined connectivity experience in the same way that today users roam freely from Wi-Fi at home or in an office to 4G or 5G in the street. The exact same concept will be using light. IoT is a very important use case. As you increase the density and in particular power consumption, you need lower latency, lower jitter, etc. There's a lot of work that's being developed, in particular within the European projects. Elliot is one of those projects that does a lot of work on how do you actually deploy these real use cases with light communications. And you can see significant improvements in that space. There are actually 3 IEEE 802 standards that are using the light medium. Fortunately, they're all sufficiently distinct from each other. The first was the IEEE 802.11, 2019, which is basically focusing on optical camera communications. So providing ways that users or people interested in that technology can create interoperable system for OCC. Then there's IEEE 802.15.13, which is really for specialty networks, including backhauling free space optical communications. And last is really 802.11bb, which is focusing on mass market complementarity to Wi-Fi. So why 802.11? Well, basically it is the best path to mass market success for light communications and for Li-Fi. It is definitely the world's most commonly used standard. I have 3.8 billion. I believe Dorothy mentioned there was 4.4 billion devices shipped last year, and everything from TVs to baby monitors and more. So there's a really well-established, really creative, really competitive and vibrant ecosystem. That means a lot of people know what it is, how to use it, and what to expect out of it. If we are going to deploy Li-Fi on a global scale, we have to reduce the barrier to entry for anyone that wants to create interoperable systems and help grow that market. And 802.11 is the simplest integration route with the highest number of possible device integration options. So as an operational concept, it's pretty simple. The idea is that we take exactly the same waveforms and exactly the same frequency and exactly the same MAC protocols that are currently used with the 2.4, 5, or 6 gigahertz bands, but rather than operating them at their center frequency of, say, 2.4 gigahertz, as shown in the example, we bring that closer to an FC, a carrier frequency, which was whatever the bandwidth of your system is divided by 2 plus a delta. So effectively just up or down convert the traditional RF waveform to a frequency of an electrical bandwidth that can be carried through a solid state lighting source. So to that extent, there are two different architectures that are offered in terms of implementation option. The first one is what's known as a direct conversion. So you really take the information out of the what's known as the LC PHY, which in reality is the Wi-Fi 4, 5, or 6 PHY modes, and take that baseband signal and connect it directly into an optical antenna. The second approach uses this up and down conversion approach that was mentioned, which is effectively take existing Wi-Fi chipsets and just do a down conversion before sending that signal into the optical light antenna. Okay, this is really simple because you have a very large availability of devices that you can use as a baseline to try and create a Li-Fi system. There's the clear channel assessment is really important, and the important is that it's identical to what Wi-Fi 4, 5, and 6 use. So there's really no change to the baseline chipsets and devices that you can buy off the shelf today. However, 802.11bb does suggest the implementation of what's known as a Li-Fi repetition approach, where Li-Fi access points effectively immediately retransmit the received signal from a user device using, for example, amplify and forward or other approaches to support the clear channel assessment, and in particular, the CSMA channel access mechanisms that are defined in 802.11. Remember, the fundamental difference is that in 802.11, every station can hear every other station. So the hidden node problem is typically not that common. With light, because you have a very directional device from the user up to the access point, two user devices very rarely, if ever, hear each other. So they both assume that the channel is free. So you need some mechanism that will help articulate that the channel is actually busy to the users, to the user devices, and thereby prevent the hidden node problem. Again, the use of OFDMA into Wi-Fi 6 is really important because it naturally provides a possible scheduling mechanism to avoid these types of channel access collision issues that might be happening. We also support spatial multiplexing and wavelength division multiplexing. We specifically define two buckets effectively for WDM. One is between 800 to 800 to 900 nanometers, and the other is 900 to 1,000 nanometers, where the entire operational range for 802.11bb is between 800 to 1,000 nanometers. And the reason for having these two buckets is because of the availability of current components in the solid state lighting space, whether that's infrared LEDs, photodetectors, avalanche photodiodes, or VCSELs. There's a plethora of devices that can help support communications in this spectrum. Of course, there's also then spatial multiplexing, which allows the transmitter to support different areas out of the same access point. So if you think of two antennas in a traditional RF context, the two antennas will typically provide overlapping field of coverage, say in the 5 gigahertz spectrum. With light, each antenna would cover its own section and therefore extend the coverage area of an access point, as an example. So both of these mechanisms are supported with 802.11bb. So where are we with the timings? Well, 802.11bb is done from the working group perspective. Draft 7.0 passed with 100% approval rating, and we're looking forward to the next steps within the IEEE Standards Association Standards Board for final approval. Ideally, we'd like to complete that process over the course of the next few months. but effectively, the standard is available for anybody that would like to buy it on the IEEE Explorer store, and you can build products to it. And in fact, there are already some products that are pre-standards compliant, but are actually now standards compliant, I guess, if we can say that. The one thing that I do want to bring to everyone's attention is that there is also this Light Communication Alliance that has been formed. And really the idea is to try and create an ecosystem of industry partners that will help, number one, articulate the different technologies that operate in the light spectrum, and number two, articulate the value of using light communication for a variety of use cases. If you are interested, please reach out, and we are very happy to work with anyone that has a true interest in light communication. So next steps, continue with the education on the Light Communication Alliance and on the benefits of Wi-Fi to the wider world. Of course, look at the potential integration with Wi-Fi 7 as that is coming out for future iterations of 802.11 light communication standards. And of course, there's a need to identify certification bodies for any light communication devices and define these structures and technical requirements. These are the references, and thank you for your time.
Hey, thank you, Nicola. Thank you so much for sharing with your audience about the great work of the light communication. We have a question. The question is actually asking for light communication or the Light 5. It is mainly focused on the indoor applications. Can it be used for outdoor also? So this is a general question that one of the audience wants to know.
Yeah, so definitely light communications as defined in 802.11 is primarily for indoor. However, in the same way that you can take a Wi-Fi access point and put it outside and it'll work just fine, you can do the same thing with light. The difference is, of course, remember, between free space optics and Li-Fi, what use cases are you targeting? So in theory, you can take the same concepts and apply them to point-to-point communications, but really the 802.11 BB standard focuses on indoor communications.
Okay, great. And another quick question, because I also want to give more time to Mark. Because you say in this slide now that you want to integrate the Night 5 for Wi-Fi 7. And audience want to know what is your direction of the main challenge for the integration. Is there any challenge, or I should say in this way?
Yeah, I mean, I think there's definitely challenges. There's a lot of things that are happening with respect to Wi-Fi 7 that may or may not be directly applicable to Li-Fi. In particular, the kind of MLO, multi-link operations, is a key feature, and it is not yet clear of how multi-link operation directly translates to Li-Fi, or if it does or if it doesn't. And of course, there's always the challenge of actually building products and how that up and down conversion can be done more or most efficiently. So yeah, there's a lot of practical challenges in addition to some of the standardization challenges.
Awesome. And one last quick question from an audience. So actually the audience asked, is there any specific or any new Mac features in the 11BB that you can quickly just give all of us a quick introduction?
Short answer is no. There are no new Mac features other than the introduction of the kind of repetition mechanism, which is again suggested for operations, but there's nothing that changes the baseline 802.11 Mac for use in the light spectrum currently.
See, that's why it is more easier for the integration to the mainstream Wi-Fi, right?
Exactly.
Awesome. Thank you, Nicola. Thanks again for the great work. Thank you so much.
Thank you for the opportunity.
Yeah, so now we have our first speaker, Mr. Mark Ammerman. Mark is a senior researcher at Fraunhofer Focus. He is currently the research lead wireless networks and the 5G testbeds and infrastructures in the software-defined networks department. As a freelance consultant representing various telecommunication industry players, he has over 20-year experience in bringing research and innovations into standards, particularly in the area of next-generation networks. Mark currently serves as the chair of the 802.11 Task Group for Enhanced Broadcast Services, also known as the TGBC, and he also chairs the 802.11 Coexistence Standing Committee. Mark, thank you very much. Please share with our audience the great work your task group is doing. And now you have the floor.
Edward, thank you very much for the introduction, and thanks for spending your time here for a short overview and introduction to our newest amendment on enhanced broadcast services. Please allow me first to also acknowledge and thank the co-authors and colleagues who significantly participated in the creation of the standard and, of course, contributed technically to this presentation and the work that you will learn about in the next few minutes. So, as a quick outline of our talk today and maybe of 802.11bc enhanced broadcast services in a nutshell, what are the three key main things to remember, key features of the new amendment? 802.11bc defines enhanced broadcast services and enhancements in particular for the downlink and uplink data transmissions via broadcasts. It provides services that enable an efficient distribution of content to a very, very large number of consumers in the local neighborhood of your network. It supports a power efficient zero configuration scheme for delivering data to remote destination, and in particular supports unassociated and associated stations at the same time. Coming back to the question that one of our audience had on the last presentation, so 802.11bc is clearly scoped to work MEC enhancements only. We do not work on any PHY changes. In particular, we were scoped to avoid any changes to existing chipsets, which has a major advantage. So BC can immediately be rolled out on existing legacy devices via firmware updates. So with that general framework of the talk in mind, let's have a quick look at 11bc in detail. So we target as a use case for downlink support for associated and unassociated stations. In the beginning, we looked at video streaming in large stadiums where the audience wants to receive a highlighted replay of the soccer or football game, have video from the game from different angles or different sports activities in parallel. Also, a very dominant use case is the timetable distribution at stations or airports, or multilingual audio services at museums. Also, emergency instructions that are available at the shopping mall and are broadcasted via Wi-Fi to phones located within the shopping mall are in the scope here as one particular use case. And of course, broadcast services enable intelligent transportation broadcast services for non-safety critical environments. Apart from the pure downlink services, one key feature also supports unassociated stations that want to distribute information in the uplink direction towards a service in the cloud without the need of being associated to an access point. Dominant examples here are, for example, asset tracking, where you can use inexpensive, low-power multi-trackers that ping a service in the cloud, for example, to provide information on the location of your baggage, inventory tracking, or parcel tracking. Also, such uplink broadcast services allow zero configuration of low-power sensors, which simply are deployed in the field and then use uplink services to contact their configuration server without the need of any additional configuration and access schemes for existing Wi-Fi networks. So all of those use cases, of course, have not only technical feasibility, which was proven before we started the project, but also commercial feasibility. So all these use cases represent a total potential market of more than 20 billion connected devices in the sensor and broadcast deployment area. And initial research indicated that this results in an estimated worth of $2 trillion for the corresponding market, which of course gave us a pretty significant backing in the beginning from infrastructure operators providing services in stadiums, museums, schools, universities, device manufacturers for producing sensors, mobile phones, or IoT devices, but also resulting services at the higher layer for broadcasters, event organizers, IoT operators, or private end users and commercial end users in the consumer market. So with all of that, what did 11BC in particular work on? What are the key features that you will see in the upcoming next amendment of the Wi-Fi standard? Well, obviously, one of the most important features is to detect that there is a feature and a service available. So we provide service discovery, negotiation, and termination, which enables the station to find available broadcast services that can be received with or without access restrictions. So on the left side, you see a typical frame exchange that your Wi-Fi device conducts today when associating or discovering available access points. Regarding the broadcast service amendment, you have the ability to probe an access point via probe request or responses to detect the availability and also to request the access point if there are any broadcast services supported by this access point and available here. So this is purely for the public announcement of services with corresponding access requirements, which are also broadcasted from an access point periodically via the EBCS info frame. So once you know what services are available, you might want to request services which are publicly available without any association to the access point, which can be done with the EBCS content request and response, which results in the corresponding EBCS data transmission. So in particular, the service negotiation supports associated stations via the EBCS content request response framing, as well as the unassociated stations, where you can use ANQP packets that can be transmitted to the AP without the need for corresponding associations to request and access the corresponding services. Also, as additional features, we discussed in the group and implemented in the standard means to terminate corresponding services in the case a station does not want to receive those broadcast information anymore, which allows the AP, the access point, to decide if the service needs to be continued being broadcast or not, which of course is a significant aspect in implementing power saving mechanisms. Also, we have means of enabling an easy change of the AP you reside in by having reduced neighborhood reports, providing you information on the corresponding discovery and services available in your next AP. So now have a more detailed look at the downlink broadcast of content. So first, we have a general setup in which we have servers located in the cloud, access point forming the coverage area of 802.11 networks, and the receiving stations. So the content servers may be located externally in the cloud, and they are the originator of an identified or tagged content that is to be broadcasted towards stations within the access area of the access point. The access point here is in control and charge of the information that is made available within its coverage area. So it may request the stream from the server, and this actual request mechanism is out of scope of the standard. And of course, the operator of the access point inherently decides which services are broadcasted, which is also a management and security aspect that we considered in the amendment. Then the broadcast stream is provided to associated or unassociated stations. And in order to convey to the stations the information about a specific content of a broadcast stream, the AP may map the content stream to a 802.11 specific content ID that is then later on used to build a special multicast MAC address. Finally, the broadcasted information is received by the stays, and using that previously built special MAC address, the stays may employ MAC address-based filtering to decide if they actually want to receive corresponding information and forward it to the upper layers, or just simply discard the information received via the broadcast service. So for the interested people, a quick deep dive how that is done in terms of mapping the broadcast stream to a specific MAC address. 802.11 BC uses here multicast addresses, as you can see on the right side. We start with the OUI for 802.11 frames, and then the remaining octets are used in the downlink direction to provide information on the AP or group of APs which broadcast a current traffic stream, and the final two octets are used to contain a content stream ID which is by the AP mapped on the specific broadcast services made available. For the uplink case that we will look at later on, the entire six octets are used to indicate the basic service set ID addressed in order to forward information in the uplink direction. Also, in the downlink direction, EBCS provides content origin authentication and hence prevents fake AP attacks. For that, EBCS supports 3 types of one-way frame authentication mechanisms that do not require key negotiation. They are namely PKFA and HCFA, that both schemes can be used for specific use cases and applications. PKFA uses a public key algorithm to authenticate the frames, and each frame contains the certificate or the signature that enables the receiver to authenticate the frame and the origin of the frame. This is usually an application which is good for small data and time-sensitive data. Also, a second scheme supported is the hash chain frame authentication, which uses a public key algorithm and one-way key chain. And this one-way key chain is a lightweighted frame authentication mechanism that only requires a hash value calculation. And this is in particular used for streaming applications. Also, as a generic services, EBCS provides higher layer secure authentication, which is a generic concept that higher layer protocols may be used to provide corresponding authentication, which is out of the scope of our standard. Also, looking at the second major use case, let's have a look at the uplink broadcast services or uplink relaying services. In that case, the uplink relaying services provides means for a device to send short data to a cloud service without the need to join or associate with an access point in its network. The frame carrying the data is broadcasted by the device and includes the address of the destination, potential security parameters, and the ID of the device. Also, it is important noticing that the relaying services is best effort and is targeted to serve low power, low cost devices. The transmitting device is not required to spend power in monitoring the wireless medium to determine if there is an access point in range or not. It may simply broadcast its information. Also, in addition, the relaying AP might not forward the received message to the server in the cloud based on selection criteria deployed and employed at the specific APs. For that, there needs to be an agreement for uplink relaying services between the relaying AP and the potential cloud service provider. An AP or the operator of the AP thus needs to have an agreement with a specific destination to support such relaying services, which is really important to reduce the possibility of DOS attacks. Also, the criteria may include authentication the transmitter, checking replay, and limiting the amount and frequency of data being sent upwards towards the cloud service. Thus, deployments can have a centralized controller sitting behind multiple IPs at a location, or they may have a distributed approach implemented at every IP. Based on this agreement, an IP can embed additional information such as date, time, or location of the AP into the uplink service data provided to the cloud service. So with that, let's, in summary, have a look at 11BC. 11BC provides enhanced broadcast services, advances the support. I think I'm on the video right now, apologies. So let's quickly go back there. Okay, so basically, concluding the talk today, you see a short field trial demo here in which we have an AP which broadcasts a video stream of a tiny toy train. The AP starts the transmission, and here in the room you have roughly 100 devices which are not associated to the AP and quickly pick up on the broadcasted video stream and display that on the corresponding monitor. So with that, a quick summary and conclusion. 802.11bc Enhanced Broadcast Services advances the support of the transmission and reception of broadcast content. It supports stations while associated or unassociated in infrastructure basic service set. Content can be relayed in the uplink and downlink direction to and from external servers. And it adds specific features allowing the access point to control the relaying process, to avoid DOS attacks, stations to filter relevant information, and provides original authentication that prevents fake AP attacks. The features are Mac only, that is, the silicon is not changed, and thus enable fast rollout via our firmware. In case you're interested and want to learn more about the technical details, 11BC Draft 7.0 has received 100% approval rate, is ready for final publication by the IEEE SA, and is also available in the IEEE web store for purchase. So with that, let me thank you for your attention, and I'm happy to answer questions. Edward, thanks.
Yes, Mark, actually, there's one maybe quite technical question ready for you from an audience. The audience actually say that from their understanding, 11BC aims to allow the client device to broadcast the data to other client device, no matter they are associated with an access point or not. So in this case, how it is similar to TDLS?
So what we support here, really, that was the biggest challenge, is to support broadcasting of uplink and downlink services at the MAC layer for 802.11 devices. So before we had .11BC, basically no matter what protocol or mechanisms you employed in a .11 device, that was not possible for standard phones that you have in your phones or standard computers that you have with you. The only exception that you could think of are the OCB or 11P out of band configurations for the automotive sector, but those have a very specific firmware implementation for the services and provided everything in the higher layer, which makes it almost an orthogonal implementation. With BC, we basically provide standard commercial off-the-shelf consumer chipsets with the consumer firmware, with the ability to do this up and downlink broadcasting. Also, another aspect that I just see in the chat window, another question from the audience was on the number of BC devices. So basically, there are limitations which are vendor and implementation specific regarding the number of .11 devices that you can support in a specific access point. It's still a large number, but there is a limitation. With BC and no need to associate to a stack, you basically waive this limitation at all. So once an AP broadcasts information or traffic streams to unassociated devices, there is no limit on the number of .11 clients that may receive this information.
Okay, awesome. Thank you, Mark. Actually, you also answered the question that I want to ask already. So it's good. Thank you so much, Mark. So actually, we may have 1 more minute for anyone of the audience here who want to ask any speaker any question. And actually, Dorothy, we may have a question for you. There is an audience asking, because in your presentation, you mentioned something like the new project after the Wi-Fi 7, like the Wi-Fi 8. So the audience want to know which group is actually working on this and what kind of, and do you have any pointer to the audience?
Okay, yes, Edward, can you hear me?
Yes, I can hear you loudly. Thank you.
Okay. The question, yes, is which group is working on, quote, Wi-Fi 8? So this would be the work which is the next MAC and PHY amendment beyond 11BE, which is Wi-Fi 7. And this work is ongoing now in the ultra-high reliability study group. This group is defining the boundaries of the project and their goals for the next MAC and PHY, which most likely will be known as Wi-Fi 8. This will be the task group BN project, which the task group itself is on target to begin work in November.
Okay, great. Thank you so much, Dorothy, for the useful information. So, and I do not see anyone in your chat box for any question. So once again, I would like to thank Dorothy, Nicola, and Mark for joining us today and sharing what is going on in the world of the 802.11 for Wi-Fi. A quick programming note to all of you. The Computer Society will host 3 different webinars from later today to April 18th. At 8 p.m. Eastern Time later today, you can join us for a special night presentation with our society's leadership. Each leader will give a short presentation on the topic of interest relating to computing. After that, they will be available for a short Q&A as well as an Ask Me Anything session. On April 13th, you can also join us for a rapid fire session, how to stop wasting time in meetings, with professional advice on making your next meetings more efficient. And lastly, on April 18th, our society's Vice President of Standards will deliver a standards webinar, You Don't Say, Standardizing Inclusive Language, which considers how terminology emerged for new technology, why some technical language is being identified as non-inclusive, and why there are ways in which people resist change in language. Finally, once again, I would like to thank all of our speakers today and our society staff for joining us, and for all of you for attending and for this lively Q&A discussion. Thank you again, and have a great rest of your day. The webinar is now concluded. Thank you so much. Bye-bye.
Thank you, Edward. It's been a pleasure.
Thank you.
Thank you very much, Edward.